Hi, this is David. I am a research fellow with the Division of Mathematical Sciences. Today, I will continue to be your tutor. But starting from Chapter 3, 6 of my colleagues will take over me to present the homework solutions in this video recording series. Now let's review what we learned in Lecture 2. First, we learn some basics of logic. In particular, we learn proposition and paradox. So proposition is a statement. It's a declarative statement. And it has a result that is either true or false. And for paradox, it is also a declarative statement. But what is different from proposition that we don't know whether it is true or false. And we learned some logic operations. And here I want to highlight 3 basic operations we learned. It is the AND, OR, and NOT. And the second part, we learned some important laws used in logic. For example, the De Morgan law. It says that the knot of P and Q is equivalent to not P or not Q, and the knot of P or Q is equivalent to not P and not Q. And we learned commutative law is that we can swap the order of the operand, say P and Q is equivalent to Q and P, and the P or Q equivalent to Q or P. We learn distributive law. It says that P or parenthesis Q and R is equivalent to that I put P and Q together, and I put P and R together, using the AND operation. And likewise, we have P and parenthesis Q or R is equivalent to P and Q, P and R, and finally O. And we learn absorption law. it says that P and P or Q is P, and P or P and Q is P, is equivalent to P. That means I have P here, I got P, I have P here, I got P, and the operation is as here I got O, here I got N. Similarly, here if I put and here I made a mistake, it should be N, and this should be O. So that it says if it is and this thing is O, then I got P. And then we also learned new logic operations. One is the conditional operator. That is, if P and Q written as P to Q equivalent to not P or Q. And we learned the biconditional operator is that if and only if, that is P Q, if and only if Q is defined as P to Q is true and Q P is true as well. Now let's talk about the last part. That how to use inference rule to argue true or false. So here, argument means that I give you some premises, that is some statements, and you draw a conclusion. This is the last statement of an argument. And by using inference rules, I mean I input some statements or some premises, and by the rules we can finally return a conclusion. For example, I give you P and Q is true, then we must have P is true. And if I give you P is true, then we can have P or Q is true. And if I say if not P, then false. Then what do we have from here? Is that we know P must be true, because this inference means that not P must be true. So that means P that is saying not P must be false. So P must be true. Okay, so that's all for the recap. Okay, so now let's talk about the homework. For question 1, says 2 plus 2 is 5. Is it a proposition? It is indeed a proposition. Why? Because this statement always true, always false. And the second is 2 plus 2 is 4. Is a proposition? Yes, because this statement is always true. So this thing says x equals to 3. A proposition? No. Why? Because if x is 3, then true, right? And if x is not 3, false. So we don't get a unique answer. So this must not be a proposition. The fourth subproblem says every week has a Sunday. It is true. Because this statement is always true. So it is a proposition. And for the fifth problem, have you read Ch2, Ch22? A proposition? No, because it depends on who answer this question. Sometimes it is true, sometimes it is false. So this is not deterministic, whether it is true or false. So this is not a proposition. Now let's talk about Q5. if I ask you to verify not P or not Q or not P and not Q is equivalent to not P, and of course we can use truth table to show that the left hand side is indeed equivalent to right hand side. But this method is indeed a little bit stupid but simple, and here we can use the better method which saves you more time. Is that we try to develop a series of logical equivalence by using the inference rules. So the starting point should be this thing. Okay, you can have copied the left hand side here. And first, we try to simplify this thing using the De Morgan law. We can have negation P O Q. Oh, sorry, and Q here, and the rest part remains unchanged. Now let's try to observe what do we have. You can find that not P here, not P here. So, and this is OR operation, but this is an AND. So, are you familiar with this format? It is indeed. We can use the distributed law to simplify this logic equivalence as not P and Q or not Q. So why I'm doing this thing here? Because by distributed law we can say we can put not PQ here and not PQ here, not P and not Q here, and using the odd operator here, and by observation we can have Q or not Q must be true. So it is either true false or false truth. Anyway, it returns true. So, and something and true means something here. And this is indeed the right hand side in the problem. So then we are done. Now let's talk about Q7. Ask you to show P or Q inverse R is equivalent to P inverse R and Q inverse R. So of course you can use truth table, but I don't like the truth table, it's too slow. So let's use a faster way to do it. So P or Q inverse R, that is saying by the conversion we know the negation of a P or Q and R, and by De Morgan we know not P and not Q or R is here, so be careful with the parentheses. This thing is equivalent to this thing. Okay, so now let's continue using the but definition should be by the conversion theorem, it says should be not something or, and that is not something or. Okay, so let's continue. As by using the distributive law, we put not P or R together, and we put not Q and R together. And in between we are using the AND operation. So again, by the conversion, we know this thing is P inverse R, right? Because P inverse R means not P or R. And likewise, we have Q inverse R here. So finally, concatenated by the AND operation. So this is indeed what we want, right? So we finally proved this thing. Let's move on to Q8 to verify P first Q or Q inverse R is equivalent to P inverse R, whether true or false. And we can do this by starting from the left hand side. Okay, so by conversion we know this thing is not P or Q. And this thing is not Q or R. what is the next step? By observation, we know that the operators are all the logic all, so you can use the associative law to put things like as this format. So that means I put Q, not Q together. The special thing about this part is that it must be true. So if in the OR logic we find something is true, then the result must be true. Okay, but the right hand side says it is P inverse R, so they are not equivalent. So this statement must be false. Let's talk about Q11. Well, Q11 is a bit complicated. So we have some arguments. Is that not P inverse R and not S? And T inverse S. U inverse not P, not W. U O W. And with this premises, and it claims that T inverse W is true. So how can we verify that thing? So the idea is that try reasoning from the simplest argument so what does it mean by saying the simplest? Is that here in our example, this thing is simple. Okay, because we only have one variable. So let's number these arguments. 1, 2, 3, 4, 5. Okay, so from 4 we have W must be false. And with W, now let's move to something that is related to W, that is 5, right? So from 5 we have U O W, that is U O F, that is U. So this thing is true. That means U must be true. So now we have two things clear. Now with U and W. Now what's the next So it's number 3 because U is here. So we know U is true. So from 3 inverse P, that is saying true inverse not P. So what does this mean? So if it is true, then this thing must be true. So that is the same way of saying, well, here, okay, that is P must be false. Okay, we got the third variable clear. And now we know W, U, and P, and we have 2 premises we don't use. So let's try to start from the first one, because for the first one we at least know one of them. Let's trying to figure out the relationship between R and S here. So we try to figure out R and S, given that we know P is false. So we start here, that is from 1, that is not P, inverse R and not S. So by conversion we know not P, O, R, and not S. So this thing is P, O, R, and S. And we know P is false, so put false here. And so false is here, so it has no effect. So that means it must be equivalent to R, not S. Okay, this is the magic here, you see. And this thing must be true. And we had an AND operate. So we must have R is true and not S must be true. This is a unique solution here. And essentially should be bidirectional. Okay, so this gives me okay, so we further know R and S. And finally we can learn from 2, that is T inverse S. So we know S is false here, so that is T inverse false. So what is T? So we can infer that T must be false. Okay, if T is true, then this statement is false, so it's a contradiction, so T must be false. Okay, now we put everything together. We know, here, we know W is false, and we know T is false. and what do we want to argue? So the conclusion says T inverse W. Okay, so that is we know T is false and W is false. So false inverse false. This is indeed true. So this is a valid conclusion. Okay, then we are done. Now let's argue the final question. Well, it is another complicated question. So we try to ask you to determine the following argument is true or not. Is that I give it P and P or Q inverse R inverse S and T inverse R. Okay, so let's label it as 1, 2, 3, 4. Now it says that not S inverse, not T. Now let's verify. So first of all, let's simplify the conclusion because I don't want a not here. So this thing is equivalent to T inverse S, right? Okay, so and we start from the simplest argument is that the first argument, we know P is true. And now from 2, 1 here. So, okay, from 2, we know P or Q is T or Q. It is. Well, so this is always true, right? Because this is a OR operation. In other words, so Q is either true or false. We don't know the value, but it can be either true or false. Okay, so then from 3, we learn Q inverse R inverse S. So now let's use the if else statement to argue this thing. So we know that Q is either true or false. So first I argue that Q is true. And then from here I have T. This thing says T inverse R inverse S. So we must have this thing must be true. It cannot be false. So R inverse S is true. And if Q is false, it's another possibility. So that is false inverse R versus S. So this thing, this time if it is false, so it can be either true or false. So we don't know. It can be true or false. And this thing must be true. Okay, so let's follow this argument. So if let me repeat here. So here we have two possibilities. So Q can be either true or false. So if we go this way, then we find that T inverse R inverse S. So that means R inverse S must be true. Otherwise, we can argue that we have false inverse R inverse S. So if it is false, so then this thing can be either true or false. We don't know the exact value. And if Q is true, and we know S must be R inverse S be true, and from the false premise we know that T inverse R must be true, right? So we put them together by transition. We know T goes to R and R goes to S, so T goes to S. This thing must be true. Okay. So, and if it is true, well, this is what do we desire, right? Because the conclusion is at T inverse S, and now we have T inverse S. So this way, correct. And now let's check if Q is false. Is this still correct? So if Q is false, so then R to S can be true, and R to S can be false. We don't know. So if we go this way, and we know here that T inverse R is true, so same way we can argue that T inverse S, so it is correct. And if we go this branch, R inverse S is false, and we know that T inverse R is true because it's from the false argument. And now we need to take a closer look at this premise, and this actually means that if this statement is false, what does it mean? So if it is false, we only have one possibility for R and S. You see, so this way R must be true, S must be false. So only one possibility. And from here we put this conclusion into false premise. We have and this gives me T inverse true, and this gives me T is either true or false. We don't know. Okay, it's a little bit messy here, so now let's summarize this branch. We have P is true. And we have Q is false. And we conclude that, well, let me check. So we can conclude that R is true, S is false, and T, the value of T is not determined. So let's put things together. R is true, S is false, but we don't know T, the true or false. But the conclusion says T infers R, T infers S. So let's check the value of T infers S. Okay, so S is false, so we have this T infers false. And because T has two possibilities, so indeed we have two branches here. It's either true inverse false or false inverse false. This is true, definitely, but this thing is false. Yeah, this is the, what do we want? This is a counter example here. So that is if I set P true, Q false, R true, S false, but T as true, this thing, and we don't use it, we just use this, and this gives me T inverse S does not hold. It is an invalid conclusion. So to sum up, the argument of Q12 is false, because we find a counterexample to show that it is indeed false. Okay, that's all for today's tutorial. Thanks for watching. Have a nice day.